Hey guys, today we're going to continue looking at Unit 12, and we're going to look today at binomial experiments. We're going to start getting more into different types of samples and different types of probability. Binomial experiments are something that are very special. They are special and they're unique because there are these three important features. The first one is that there are repeated trials. So it's not that I'm going to do I'm going to do an experiment one time and then stop. I'm going to do this several times. It's something that can be repeated or replicated. The other thing is that there are two possible outcomes, and we call them success or failure. So, for example, we could say flipping a coin, getting heads or tails, where we would call it getting heads the success and tails the failure, or vice versa. We could say something like, what's the probability of getting an even number on a die when you roll it? Because either you get an even or you don't get an even. So it's either a success or a failure. And failure doesn't mean necessarily a bad thing. It just means that it wasn't what we were looking for. So it could be how many people failed a test. And since we're trying to count how many people failed, the success would be if they failed, and the failure would be that they didn't. So just be careful with that language. Don't associate failure with something negative. And then also the final thing is that the probability of success is constant throughout the trials. So like with flipping a coin, the probability of getting heads is always going to be 0.5. The probability will always be 0.5 for flipping a coin and getting heads. So those are the three characteristics that make something a binomial experiment. So here's an example. A store is running a promotional where they give away scratch-off cards. 40% of the cards have prizes. Suppose you have 3 cards. Find the probability of getting 3, 2, 1, or 0 prizes. So first of all, let's look at these. There are repeated trials. So I have 3 cards. I'm going to do this 3 different times. The second thing is that there are only 2 possible outcomes, success or failure. In this case, my success would be that I get a prize. A failure would be that I don't. And then the final thing was the probability of success is constant throughout trials. They've told us that 40% of the cards have prizes. That 40% is not going to change. So we need to find the probability of getting 3, 2, 1, or 0. Okay, so let's start with the probability that none of these are winners. First of all, let's look at how many different combinations are there of possible outcomes. Well, I could have that they all are winners. So let's do win, win, win. I could have that they all don't win. So I'm just going to use F for failure. It could look like this. It could look like this. And basically, I could keep listing these, but what we should see is that there are only 2 possibilities for each one, for each card. It's either a win, or it's either a success, or it's a failure. Either I won a prize or I didn't. So on the first card, there are 2 possible outcomes. And then the second card has no bearing on the first one. Like they're independent of one another. If this one was a winner, it doesn't mean that the next one's going to be a loser. They're independent of each other. So the second one still has the same probability. It's got this times 2 probability. And then we've got times 3, or a third one that could be either a winner or not. And when we multiply all those together, that's the same as doing 2 to the third. So I'm just saying there are 2 possible outcomes with 3 cards that I'm getting. And that would give me 8. So the probability of getting exactly 0 would mean that all of them were not winners. And there's only one possible combination where that happens. And so that would be 1 over 8. So if I wanted to do probability of x equals 1, I would do how many of these have a winner for 1. Well, if I look at my combinations, I could have if I just list them all out real fast, 3, 4, 5, 6, 7. I'm missing this one. All right, so if I'm looking for combinations of cards that have one winner, exactly one winner, I've got one here, and one here, and one here. So there are 3 out of 8. It's almost like the probability distribution that we were doing at the beginning of this unit, where we were just looking at how many of these make this be a true statement. 1, 2, 3. And then if I wanted to see what's the probability of all 3 of them being winners, it would be 1 out of 8. Okay, so there's our probability of getting 3, 2, 1, or 0 prizes. But what we're going to see is that we are repeating this. So these are independent trials. Again, they're independent because if the first card is a winner, it does not mean that the next card is inherently not a winner, or it doesn't mean that the card is automatically also a winner. They are independent of one another. They each have a probability of success p. So in the last problem is 0.4. That means there's also a probability of failure, which we call q. So these have to add up together. So in the last problem, if 40% is the chance or the probability of a card having a prize, that means that it has a 60% chance of not having a prize. So then we're going to calculate the probability of x successes. We're saying x is the number of successes in n trials. How many trials are we doing? Is given by this formula. Now, this right here might look a little bit new or different to you. And to calculate NC6, this is just calculating a combination. It means that we are going to take n factorial over x factorial times n minus x factorial. For a little bit of review, in case you don't remember, factorial means, if I have like 5 factorial, it means that I'm going to take 5 and multiply it by every number that comes after it. So in this case, that would be 120. If I have 3 factorial, it's doing 3 times 2 times 1, which is 6. So that's what factorial means. So we're going to practice a little bit more with this now. So here we are given x, n, and p, and we need to calculate the probability of x successes. Oops, I have that written twice. Sorry. In n trials for the given probability. So I'm going to use this formula right here. I'm going to say, come on. There we go. NCX. He's not. There we go. And then P to the X, Q to the N minus X. All right. So when I plug all these things in, I have 5. We read this as 5 choose 2. 5 choose 2 times P to the second power. Except let me replace P. I already know what P is. I'm sorry. 0.25 to the second power. And so if my probability of success is 0.25, my probability of failure, again, failure not meaning a bad word, but of just not a success, is going to be 0.75 because these have to add up to 1. So I'm going to put 0.75, and then it's going to be to the n minus x. And what should happen is when I simplify that, I'm going to get a 3. Notice that these two numbers here add up to how many total samples I'm taking or how many trials I'm doing. So when I calculate the 5 choose 2, I'm going to get 5 factorial over 2 factorial. Come on. Sorry, guys. 2 factorial, 5 minus 2 factorial. So I'm going to write this out. 5 times 4 times 3 times 2 times 1. So this would be 2 times 1 here. And this would be 3 times 2 times 1. And so if you want to multiply all that out, you can. Since these are being multiplied, I can also simply cancel these out. But if you want to multiply the numerator and then divide it by the denominator, that's fine too. What I'm going to get is 20 divided by 2, which is 10. So that's for the 5, choose 2. So I'm going to get 10, oops, I zeroed in it right, times 0.25 squared. That's going to give me 0.0625, and then 0.75 cubed gives me a longer number, 0.42. I'm just going to round it. So when I multiply all those three numbers together, I'm going to end up with 0.26, we'll call it 264. You can double check my math, but that's what your probability is. So if you translate that into a percent, it would mean that there is a 26% chance of getting 2 successes out of 5 trials with a 25% probability. Try the second one. Work together as a group or work on your own, wherever you're at, and come back and we'll check our answers. Okay, I drew a line to try to keep it separate, but here's the work that I got. And you should have gotten a final answer of 0.2375. Let me show you what I did. So I plugged in my x and my n. Oh my goodness. And I did 10, choose 8. So here's my work for that. And this is where your work might look a little bit different. You might have just plugged it in your calculator, and that's fine. What I did was I said, okay, I can do 10 times 9, and I can actually stop at 8 factorial. 8 factorial, remember, is 8, 7, 6, 5, 4, 3, 2, and 1, all being multiplied. And what I did was said, oh, I can cancel out 8 factorial and 8 factorial, and that's going to work. But I'm going to have 10 times 9, which is 90, over 2, and that gave me 45. Again, you may have written it out differently, and that's okay as long as you got to the same answer. So then I plugged in my 0.7 for P, and to find Q, I was doing 1 minus P. I was doing 1 minus 0.7, and I got 0.3. And then I checked my exponents did add up to be 10. They should add up to the total. And when I multiply all those things together, depending on how you rounded this number right here, you may have gotten a slightly different answer, but it should have been somewhere pretty close to 0.235. So that's all we're looking at today. If you have questions, you can let me know, but I would also encourage you to look at some of the resources that you have at your disposal, like your textbook. And like I said, let me know if you have questions. We'll go over this a little bit more tomorrow and look at it together. Here is your homework.